Those are the codes we are going to use today. Last session, what we did was basically to establish more or less the theoretical framework. Very basic theoretical framework we use to base our work when we run cosmological and numerical simulations for embodied problems. They mean cosmological simulations, they mean two-body simulations, they mean few-body simulations. Basically, the theoretical framework is the same. And just look at my name in Google, look at quantum quarters homepage, then you can only Google site, go to research, and then you try to download this link. The download is just right here, on the right side. Yeah? Homepage. You did it already. Okay, so yes, I mean, but I need everyone to do it in the computer. I hope everyone is in Linux because those programs are not going to work in Windows. Here, research, and here. Download. So, and this is basically the place where we left the last session. Let me finish with a couple of ideas and a couple of examples just to remind you what we were talking about in the last session. Again, last session we did it in Spanish because Euler wasn't here. Now we have to switch because she's actually here and she was trying to look at the videos and got nothing because it was Spanish. Sorry. We were talking then about the different dynamical behavior of the systems composed by many bodies. So if you have a system with many bodies, it depends on the way the particles interact. If the individual collision or individual dispersion between particles modifies the dynamics of each particle, we will call this system a collisional system. That means the dynamics of the particles is completely dominated by the individual collision between particles. Or if that is not the case, we call the system collisionless. And then we were speaking about a couple of examples. For example, we were speaking about the galaxy, where we were computing the relaxation time, which was basically the parameter we used to determine if the system is collisionless or not. If the relaxation time is long enough after you observe the system, that means that collisions don't affect the dynamics of the system. In the case of a galaxy, for example, we can make the numbers and compute the relaxation time, for example, for a galaxy like the Milky Way, And then you find that the relaxation time is of the order of 10 to the 15 years. That's a factor of 100 over the age of the universe. That means that you will need to observe a galaxy like the Milky Way for 100 of times the current age of the universe before the galaxy itself reaches relaxation. That means that in the case of the stars, in the Milky Way galaxy, collisions doesn't do anything on the dynamics of the particles in the system, and that means, for example, that if you remove a star from the galaxy, the rest of the stars in the galaxy are not going to feel it. They are not going to care about it, because the dynamics of the particles in that galaxy is completely dominated by the full distribution of mass in the galaxy, not just for individual stars. It's not like the case in the solar system. If you remove Jupiter from the solar system, you will probably destroy the full system. If you remove the Sun, of course, you will destroy the solar system. If you remove Earth, probably you will destroy the inner region of the solar system. And that means that individual bodies in the system, in this case, the solar system, are very important for the dynamical behavior of the full collection of particles. That means such a system is collisional. The same happens, for example, in globular clusters. If you compute the relaxation time for a globular cluster, you will find that it is around 1,000 million years. 1,000 million years means that a globular cluster will have around 13 times its relaxation time to relax itself. That means that have been long time enough for the globular cluster to experience a lot of interchange of energy between the particles in the globular clusters, in the inner region of the globular cluster, and that means that the collisions are actually important for those stars. Examples then about those two kinds of different systems are this one. If you are taking on collisional systems for which individual dispersion, individual interaction with the particles are important, you might think on planetary systems, you might think on the stellar clusters, open clusters, or you might think, for example, in globular clusters. You might also think, for example, in the very inner region of the galaxies. For example, in the bulge of our Milky Way galaxy, the dynamics of the neighborhood is collisional. That means that the individual interaction between particles, because the density of stars is very high in that region, then the dispersion of the particles modifies the trajectory of each star in a very violent way. So in some sense, galaxies are also collisional systems, but just in very specific regions. The very center of the galaxy, or the very center of the dark matter halo, probably is also a collisional system. Examples of collisionless systems are, for example, dark matter halos. We assume, as you know, nobody knows what dark matter halos are, but we assume, because of the dynamics or the things we observe from the dynamical behavior of these kind of systems, dark matter should be collisionless. That means that if indeed in the very center of dark matter halos the density is very high, in general the dark matter halo should be collisionless, and that means that individual interaction between particles in the dark matter halo shouldn't modify that much the trajectories of particles in dark matter halos. That's actually what we use, for example, to run cosmological simulations. As we were discussing in last session, we use, for example, this particles mesh technique and these three codes, these three methods, to run these huge simulations, assuming that the system is collisionless, because we can differentiate between collisional and collisionless systems. We can then choose for each case which approximation and which code do we need to use. We cannot use every single code for every single problem, because the dynamics is not going to be well described in any case. We can also, I think, on the dynamics of galaxies as collisionless systems, in a way that, again, for example, in order to study the dynamics of galaxies, when we run simulations under the assumption that those are collisionless systems, and for that reason we use the proper approximation, three methods or particle P3M methods or multipolar, fast multiple methods. Before we leave this thing, let me just mention something very quickly, which is going to be extremely weird for most of you, but that must be mentioned, and is the very theoretical background of this thing. The guys who were presenting the exam on dynamic, galactic dynamic, might remember this thing. And the problem is this one. When you are solving mechanical problems, when you solve the problem of the mechanics of a body in the surface of the planet, or when you solve the problem of the movement of a star in the galaxy, you might think you solve it in the real space. That means in the space you see, which is 3 coordinates, and that's all. Actually, that is not the case. Mechanically, the solution of any mechanical problem is done in a mathematical space, which is called the phase space. The universe you see, the mechanical universe you see, is described mathematically in a 6-dimensional, for a particle, in a 6-dimensional space, which is called the phase space. It's a space, mathematical space, where you can describe all of the dynamics of the system. The present, the past, and the future. You might have to remember this thing, because when you see your course in classical mechanics, you will learn it properly. The point is that if you really want to understand the dynamics of the gravitational system, you have to think on the dynamics of the system, not seen with your eyes in this real space. You have to think on that system when you see it with the eyes in the phase space, in a space which is composed by momenta and position, basically, in the most basic situation. In that mathematical space, the dynamics of the system, the complete system, is determined then by the points, the coordinates of the system in the mathematical space. And what you have to do actually is to solve an equation, this equation, which is called the collisionless Boltzmann equation, in which you are actually asking for this question, asking for the value of this function. This function is called the distribution function. This distribution function is an analytical function that tells you which is the probability to find a particle in that system in a region of the phase space. That means to find a particle in a region in this space that has some values of the coordinates and some values of the velocities. For example, if you can identify this function, then you are done. Because since you can compute the probability of finding a particle in a given space, in a given element of volume in phase space, you can identify which are the particles in space, in real space, that have a given position and have a given velocity. And then you solve the mechanical problem. Yeah? The problem is that, as you can see, this is a not nice equation, not nice at all. It's a partial differential equation in 7 variables, probably not homogeneous, because eventually you have 2 situations. Here in this square, you can have 0, and when you have 0, you have the dynamics of a collisionless system. That means you have a galaxy, or you have a matrix halo, or you have a huge piece of the universe. But when collisions appears, this equation is not 0 in this side, and then it becomes a Fokker-Planck equation, and if this one is messy, this one is even messier. Because you have to try to solve a partial differential equation, not homogeneous, and that's just a nightmare. Then, in any case, what we are trying to do, running simulations, is to identify somehow the properties of this guy, of this function. Somehow, in some way, in a quite statistical way, what we do with cosmological simulations, what we do with simulations of galaxies, what we do with simulations of the solar system, is to try to get information about this function and to try to see how does the system evolves in phase space. If you then run the simulation, you identify, for example, the positions and the velocities or the momenta of the particles in the piece of the universe, the solar system, for example, you are simulating, and then somehow, in numerical terms, you are identifying the values of that function in fixed space, and that means you are solving the problem. I just wanted to mention this because even if you don't get it, I guess you didn't. Please ask me later if you didn't. I can try to explain it better in a longer time. But at least has to be mentioned because that's actually the real way one has to understand, the real way one has to interpret all these. Today, I want we to play. Yeah, basically, there is no fun if you don't run anything. That's why I prepared a set of codes to let us run some small simulations. Nevertheless, it's gonna be very much interesting if you can try to understand what those codes are doing. We were looking at the last session. Then, basically, our problem, the n-body problem, consists in solving the equations of motion of a particle which is subject to the gravitational interaction of a given distribution of mass, also in the form of a distribution of particles. That means you are trying to solve for a given particle. You are trying to solve these equations. Yeah, which is basically the equation of motion describing which are the forces acting if you have a collection of particles. This is your system. This is the J particle. Then you are asking which is the force which is acting on this particle because of its interaction with this, with this, with this, with this, with this, and with the ith particle in the neighborhood. Yeah? Which is actually what we do here. So we are asking for the acceleration on this particle due to the interaction with the rest of the particles. Of course, this summation has to be on I different from J because you cannot interact with yourself if you're a particle. Yep. So basically, this is all we have to do. As we were discussing last time, then this problem basically split up in two main problems. The first one is then computing the forces. And that was what we were discussing last time. You use a lot of different approximations to compute the forces acting on this particle because of the distribution of mass around it. But there is a second problem, which is then compute the evolution of the system which means solving this differential equation. What we have here is actually a differential equation. And then to be able to know which is the value of the position of this particle as a function of time, we need to solve that differential equation. We want to know the position of the particle as a function of time because that's what give us the power to predict what is going to happen in the future with that particle, and give us the power to see what happened with that particle in the past. And that's all we want to solve in terms of the mechanical behavior of the system. How can we solve this thing? This is quite a messy thing. The problem is that the way this equation is written here is written in a vectorial way. That's actually 6 equations. That's actually 6 equations because if you actually speed up that thing in components you have. I mean, I can cancel this guy with this guy, and then you can cancel it and write it like x component of the j particle equals minus g summation mi xj minus xi over, I will call this thing dij. Yeah? This guy is in any way is an scalar. This is a number because this is just the matrices. The difference between two vector points in any case, general case, is always going to be a number. So it's going to be just dij the term. Yeah? And then I have just one of those equations. The other one is just the component for the x direction, which is minus g summation over I. I really want to show this thing, even if it looks nasty, or if you are wasting time, because it's actually the very way to let you understand what the codes I provide you are going to do. And we have a third equation, just for the z component, which has exactly the same mathematical form, just that only takes into account the z component of the force. Yep. Then look at this. Here we have 1, but now we have 1, 2, 3. Yeah? The result that x dot dot j equals this. Yeah? And this equals this. So actually this guy becomes basically two equations. This is for j and this is for j. Yeah? And we have the same for y and we have the same for z. So what we have here in the form of a vectorial equation is actually 3 equations of second order or 6 equations, coupled equations for positions and velocity. And that's actually what we have to solve. Then, if you want to solve the problem of the embodied problem, all you have to do is to first be able to compute the forces acting on the particles, that means solving this part of the computational issue, and second, to be able to solve partial differential equations. Who knows how to solve partial differential equations? No. Coupled differential equations. Who knows how to deal with that problem? Me neither. Then, what do we do? And look at this here. What we have here is just what you learn in the mechanics course. This is just AX equal summation of forces along that direction over M. What you have here is the same. A weight. And what you have here is the same. Yeah? What you always learn in the first course of mechanics in the university. I am not showing anything different from something you learn. But this thing is quite a bit different from the might be different from the things you have learned. There is a very easy way to solve a differential equation. A differential equation is basically an algebraic equation. It's not right. I mean, if a mathematician hears me, will kill me. But let's assume that solving a differential equation is like asking for an algebraic equation where the variable you need to to solve, to look for is different, and it's just a derivative. Let's think on it in this way. You have that the derivative of a given function with respect to time is this one. Yep. You know that this derivative is like the limit when h goes to 0 of the function evaluated in a given position minus the function divided by h. Yep. That's the definition of the limit. The problem is that, okay, then if you say, okay, I need to compute the derivative in the computer in order to solve the partial the differential equation, you say, okay, let's evaluate the limit on the computer. But the problem is that in the computer you cannot evaluate a limit. Why don't? Why you cannot do this thing in a computer? H is not equal to 0. Goes to 0 as close to 0 as you want. Maybe I choose a value of h, but you can choose another one which is smaller than mine, and you one which is smaller than yours. And so, mathematically, the limit is something you can imagine, but in the computer you cannot represent a small number as small as you want. There is a limit. At some point, h will turn 0, not because you cannot do it in your imagination, but because the computer is not able to represent arbitrary numbers. And in the case of small numbers, it cannot represent arbitrarily a very, very, very small number. That means that for the computer, we have to take the mathematical form and modify it. Dale machete, make an approximation. An approximation which is going to be very reliable is this one. I am going to say that the derivative of the function is more or less the difference of the function in two different points when h is really, really small. How small? As small as you can in the computer you have. And this is actually quite a good approximation for the derivative of a function. That means that from this equation, I can guess somehow which is going to be the value of the function I'm looking for, this one, in the future. Here it is. From this place, I can take this function, and it's going to be equal to the function at a given time plus h times df dt. And this equation, which is basically a numerical method which is called the Euler method, tells you, I can tell you which is going to be the value of this function f a small time step in the future if you tell me which is the value of the function now and the value of the derivative of that function now. Yeah? If I change, I can try to write it here. Should I do this thing? So, I can tell you that the value in the future, look at this thing, this is the value of the function in this time plus a given delta t. Because I can change the name of h to delta t if I want. It's equal to the value of the function now in the present plus the variation of the function in the present. Let's assume What you have now, or what you want to know, is the position of a particle. That means that I can tell you the position of the particle in the future if you tell me which is the position of the particle now and the value of this thing. Now, you know a lot of physics. What is this thing? The velocity. That means, if you know the velocity of the particle now, and you know the position of the particle now, I can tell you the position of the particle in the future. How far in the future? At delta t. And this thing is going to work for the coordinate x, y, and z. So, with this trick, we can actually solve these differential equations. And we can do the same for this one. We can write a similar, we can write a very similar equation for the velocity in a way that I can tell you which is going to be the velocity of the particle in the future. If you tell me which is the velocity of the particle now, and you tell me which is this thing, and what do you think is that? That's the acceleration, and the acceleration you just computed here with the distribution of particles. So you know basically all you need to solve the equation for the velocity and then to solve the equation for the position. Yeah? So here I just plug in the acceleration, and then the way we do it is first we use the definition of the gravitational field to compute the force, better to compute the acceleration, and put it here. We plug the number here, and with this number we compute the velocity of the particle 1 second in the future. And we use the value of the velocity now to compute the position of the particle 1 second in the future. That means that in this space, the position of the particle as a function of time, if this is now, and this is t plus delta t, yeah? This is delta t, then if you know the position of the particle and the velocity of the particle here, I can give you the position of the particle here in the future. And then I can move from this place to this one in 1 second, yeah? And use the information I have here for the position and the velocity of the particle to compute the position and the velocity of the particle 1 second in the future. And then I move, and I do the same, and I do the same, and I do the same. And second by second, I can then compute the position and the velocity of each particle in my simulation from now till tomorrow, or until whatever will depends on the length of the problem you are solving and the characteristics of the problem you are solving. This guy here, this delta t, is called the integration time step. Time step. It's a very important and critical quantity in numerical solution of differential equations. Look at this thing. This number should have a very peculiar characteristic. Which is that characteristic? It should have at least one very important property. should be small. Very small. Why? Because this delta t I'm using here is exactly the same age I was using here. And has to be as small as possible in order to make this approximation as good as possible. If instead of using a time step of 1 second, you use a time step of 1 day, the slope you're going to approximate for this point here in the curve is going to take you not here, but here. And then the right position is going to be here, and the one you compute is going to be there. And your simulation is going to be completely crazy. Yeah, this is a very crucial and important parameter, and we are going to play with this right now. You have a question?
It's possible to obtain a rate, for example, if a galaxy is accelerating, it's possible to obtain a negative equation.
Where?
For example, what is the center?
Here. No, the thing of the things comes for free here, inside. Yeah, if the acceleration is negative, it comes already here. Yeah, like in this case.
And the signals change to positive in this case.
Now, in the case of the gravitational field, is always negative because the gravitational force is always attractive. Yeah, but if you have a galaxy, I don't know, I mean, you are here, the reference system is here, you have a galaxy here, and then you are pulling it out in this direction, and there is another body, a huge body here, and the total forces are taking this galaxy in this direction, the acceleration is going to be in this direction, and with relative to you, it's going to be positive. Yeah, I mean, so it depends. The signals of these things are coming for free when you compute the forces in this formula. So you don't have actually to change anything in here. Yeah? This is, as I told you, this is called the Euler's method, and this is only one of many different techniques you have to solve numerical differential equations. It's not the best. It's actually one of the worst. Don't use it if you in the future are not a computer simulation of anything. Use it if you want to explain this issue to 20 students in 5 minutes. But don't use it if you want to do actual science or to want to do something right. So let's go to the codes and try to play with them. You have them. This folder, I hope, I mean you can, let's do it right. So you have to roll these use codes. So untar those files, that means you have to do tar minus xdf, use codes, .tar, yeah? And then if you do so, it is gonna inflate a lot of files, yeah? Actually, it is going to inflate you this folder, use codes, go inside please. So cd, use codes, and then you will find a set of folders. Tar minus xdf space. Use codes.tar. No. So, sorry, who here is not familiar with Linux commands and those things? So I'm going to make it slowly, as much as I can. No, truly. So, then the command to inflate the file is tar minus xdf, and the name of the file use codes.tar. This is the command you should have there. Ayúdame. Ustedes conocen la máquina. Ayúdame. Ya, no. Yeah, but then you say
que no me cree. No, ya hay que esperar. Casa, weón. No, pues no se ve bien.
Did you make it? This is the larger So, do you have the program? Do you have the programs? We need to work in command line. Don't do it with buttons, because you need to look at the code, file, code, change the file. So, can we go on? Can we go on?
No.
Yeah. So, let's move inside the folder. So, cd, use code, and enter is going to take you inside the folder. If you do ls, then it is going to list you the content of the folder, which are the programs I'm providing you for the exercise today, which we are not going to make to use all of them. But okay. There are 5-6 codes. No, there are actually 5 codes and a set of tools to change formats and play with it. This one here is a code which uses an approximation to compute using the direct method the force field on a distribution of particles. That means inside this folder there is a program which you can use to compute the force field in a distribution of particles using this approximation, which is, as we saw the last session, the direct method. No approximations at all. It's the exact number for the force field in each particle. This one here is the one we are going to use right now. It's a program we choose this approximation to compute the force field in a couple, in a system of 2 masses, and solve the differential equation of motion of the particles using this approximation. And that's the one we are going to use. There are actually 2 codes inside, because there is one using Euler's method to integrate the orbit, and there is another one using a deep flow method, which is a different approximation for solving the differential equation. Here we have a code you can use to integrate the equations of the orbit of a particle in the potential of a galaxy, for example. It's going to give us a very nice figure. At least we have to run it because the figure is quite nice. And this one is a tree code. In this one, we will use, or you will use, if you take the code with you to your home, we will use not this approximation for the force field, but we are going to use the one we discussed last time, using a tree code to approximate the distribution of mass, compute the multipolar field of the particles which are far away, and use the force particle-particle for the particles or the distribution of particles close to you. And in this one, I have a couple of codes you can use to move formats, because each one of those codes writes the results in a very different way, and somehow we need to move them from one format to the other, for example, to be able to visualize the results with Euler, let's say. Then, let's go first to this folder. So, CD orbit integrator. If you go and say CD orbit integrator, you will see there are some files inside. Particularly, I want you to look at this Euler.c and leapfrog.c. Those are the codes. As you can see, I'm quite an old-fashioned guy, and I don't program in Python. I'm programming in C. Because I can parallelize them here. So let's open this code and let's take a look first.
What? Euler.
Euler, yeah. Okay, no, please don't open first. Are we all here? No, it's okay. Yeah. Are we all here? So let's compile the code. I will do it from very scratch because I know some people doesn't know how to do it. So we need to compile the code. So let's do GCC -O Euler dot x. Let's put it like dot x in order to recognize it is an executable. That's actually the binary you will execute when you run the program. So GCC -Euler -O Euler.x Euler.c -lm and compile. .x space Euler.c space -lm. The problem is that compilado. Ahí lo compiló. No sé por qué. So all we have this file Euler.x. Yeah? So the very difficult part is just to do ./Euler.x and you just hit enter. And then wait for a while. Entonces desenterrar el archivo, hace solamente el tar y te vuelve a generar. So, all we have done is this. Who is not here? Jeff. So, if you look at the content of the folder this time, you have these things. Comporbit.dat. Let's see what is inside of this thing. If you look at the file, this is what we have. Look at this. This is all you're gonna thing when you run a computer simulation. Numbers. Trapping numbers. Because they don't mean anything if you don't have the ability to interpret their results. The format of this field, this field of numbers, the format in general of the file is, I have here the time, I have here the position in x, y, z, and the velocities of the particle. Let's look at the result of the simulation. Let's call it plot. And let's plot the content of the file using columns 1, 2, and 3. And then you should get this thing. The one you have here. Because I changed. Now you can see. Sorry? Yeah, this means please plot this file using methodology 2 and 3 using with plot. Try to plot. And then you can afterwards. Done. Si escribí la primera vez que ya está buscando. Por eso no, y ahí tienes que cerrar la corriente. So, does it work? Yeah. Para identificar el archivo es lo que hace Jorge con punto out. Porque a veces punto out, en general punto out son las salidas, no el bit. So, all we have this thing. Yeah, and you can see here what we have then is the orbit of a particle moving in an elliptical trajectory. Yeah? And what we did actually was to start the integration of the particle in this position and move around the focus of the conic. What is the focus of that orbit? I mean, if this one were the sun, the Earth, where should be the sun? You don't know. You don't know because you didn't configure the simulation. Nevertheless, I will show you where should be the sun. Here, at 0, 0, I do have the focus of this orbit, and here will be the focus of the ellipse. Actually, this is not the orbit of the Earth around the sun. This is the orbit of a galaxy around another one, much bigger galaxy. It's at the end the same As you can see, look at this thing. As you can see, the density of points here is much higher than the density of points here. Why? Because here we are at periastrum. Yeah? That means that here the galaxy is moving faster. Much faster. That fast, so fast that the delta t I am using is not big enough to sample the motion of the galaxy here in a very detailed way. Yeah? In order to produce much more data here, I will need to increase the value of delta t. Actually, decrease the value of delta t. So now let's change the numbers with this inside this program. So let's open the program. In order to open the program, you have to do this thing. Emacs Euler.c, the file.c, not the file.x. La 2 y la 3 son posiciones. Tiempo, velocidad, velocidad. So, if you do so, please, let's do it this way. Let's do it this way. And at the end, please add an ampersand. It doesn't show here because. Please add at the end an ampersand in order to let it free the command line. So, if you open the program, if you open the file, you will find the program. Y al final le pones ampersand. Al 7. Al 6. No, al 6. Shift 6, perdón. Sí. So, do you have the program? If you can see here, I cannot. Please open the program because I cannot make this one bigger. Yeah. Yes, I can. No. Control X. I know, but I want. Okay. Because then I will. You should. Okay, if you can see here, that's actually a program. That's a program you can use to solve to study the dynamics of a galaxy around a second one. 2-point galaxies. Because we are solving a problem which is two-body problem. We are assuming that Milky Way is just a point and blah blah blah. A given satellite of the Milky Way is also a point. You have to notice here that I compute first. I solve the problem for one particle. This is our old version of the problem. You have a different one. Yeah. No, you have the same. Okay, we have all the same traffic program. I do compute the force field. Here, look at here, I compute the distance, the point, and compute the acceleration. In x, I compute the distance and then compute the acceleration. In y, using the same formulas I had here. I'm not computing the accelerations in z, y. I'm only computing in x and y. Why I'm not computing the third? Because we know that for the two-body problem, there is an integral which is the angular momentum, and that reduces the problem to a b-dimensional problem. So I can just avoid solving the problem in the z direction for this particular case. In the very general case, in the very general situation, I will need to add two more lines, computing again the distance. I should have done this thing twice. Computing the distance and computing the acceleration along the z-axis. Yeah? And look at this thing here. What I am using here. Euler's method. You can see here the position in the future is equal to the position now plus the velocity times a given delta t, which is a parameter I can control. And the velocity in the future is going to be equal to the velocity now plus the acceleration times a given delta t, which is the same formula I have here for the velocity and for the position. The only thing is that I'm just computing the number for the position in the same variable. So I'm just updating the number inside this variable. I do the same for the second particle. Yeah? And then just print out the numbers. You see? It's very easy. There is nothing dirty besides the dirty stuff I just wrote down in the whiteboard. Let's try to play with this program, changing some of the parameters. Look at the initial conditions I'm giving for the problem. And that is actually something which is tricky. There is something very important, and is that if you really want to run a valuable simulation, you really need to understand the problem. And understanding the problem means you have to know how to configure properly the initial conditions. Initial conditions doesn't come for free. Initial conditions are the numbers you give to each of the variables at the beginning. And that means that you should know which is the state of the system at the beginning of the problem. Somehow you have to know which were the positions of those two galaxies at the beginning of the process of the simulation you are trying to run. If you can see here, I'm using first. I am assuming that there is a galaxy. I'm sorry for this. One of the galaxies is placed in the very origin of the coordinate system. You can see position in x and y is 0, and the velocities in x and y are 0. Those are the positions and velocities for the most massive galaxy in that system. Since you know, when you have two bodies interacting, the most massive one is going to be more or less placed very close to the center of mass of the system. And like in the case of the solar system, for example, the sun stays there. And all you assume is that the planets move around the sun. What I'm assuming here, in order to make this program as simple as possible, just to let us understand what is the thing I'm doing, I'm assuming then that the most massive galaxy is placed in the origin of the coordinate system. That's why here the focus of the orbit is just right here. Yeah? If I don't force the most massive galaxy to stay here, probably this orbit should be traveling around. Yeah? And we can try to do it in 10 minutes. So, as you can see here, actually I will remove this stuff. Let me tell you a history. I wrote this code 2004. And I found it just for casualty and helped me a lot because I didn't want to write this the program. But it's something very, very, very easy. Then, what you see here is that G, which is the gravity constant, for me is 1, which is the value of G. 6.72 blah 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 10 to the minus 11 newtons blah 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 blah. Yeah? 6.7 times 10 minus something is a problem for the computer. This number is very small, and again the representability of this number in the computer is gonna make suddenly, probably, that many of the operations associated with this constant go to 0 or make crazy numbers because of the round-off errors. Yeah? What we have to do then is to renormalize the system of units. And then, renormalizing the system of units, you have to choose appropriate values for the masses, the constants, the lengths, the times, the velocities, and all these things. In this case, for example, I'm using a system of units in which the constant, the gravitational constant, equals 1. Each unit of mass equals 5 times 10 to the 10 solar masses. Each unit of velocity equals 262 kilometers per second. And each unit of length equals to 3.5 kiloparsecs. Why these units? Because I wrote this program to run simulations in a context of galactic dynamics. And those are the typical units you use when you are using a galaxy like the Milky Way that has a mass in the dish of around 6 to the 10 solar masses. And typical velocities of the star are of the order of 250 kilometers per second. And the typical scale of a galaxy like the Milky Way is 3.5 kiloparsecs. So, using this, one can tweak the numbers to make the constant of gravity to be equal to 1, and then you just forget about the problem of round-off because of small numbers in your equations of motion. And then you can see here in that system of units, these are the masses of my galaxies. You can see the very massive galaxy is 15 units of mass, and the other one is just 0.43. So this is a very heavy galaxy, and this is just like a mosquito turning around the galaxy. That's why this approximation of placing the most massive galaxy in the center is working for this particular case. If you change the mass that you can do at home with this program, if you change the mass of the second galaxy, you might have to tweak something in the bottom of the program. Now, the initial conditions. You can see here the initial conditions I am giving to the second galaxy. We have position in x, position in y, velocity x, velocity y. Let's aim those initial conditions here in order to see how is the galaxy moving at the very beginning. If I have here x and y, and I have then that the initial position of the galaxy is 1,0, where should be this galaxy placed? Should be here. 1 in x and 0 in y. That's my y. Yeah, it did. Sorry. So, is it right? Yeah? Now, the velocity. The velocity has 0 component along the x-axis and 1 along the y-axis. Or should be this velocity pointing out? Zero component along the x-axis is a vector like this one. Yeah? And plus 1, because it's positive, in the y-axis should be like this. So what I am doing is throwing a particle in this direction from this position in the axis. So the galaxy should be moving like this. Yeah? Now you understand what we are doing with this problem. Yeah? Do you? Now, I was telling you that there is a very important parameter for this kind of problems, or for this kind of simulations. That parameter is the integration time step. Let's change the integration time step. As you can see, for me, the integration time step is this one. And as you can see, I choose a very small one. Let's give some very crazy number. This one. 0.001. Yeah? Please change that number. Make that dt be 0.001. Or we change the number. So please make sure that after you change the number, you save the program. So clicking in this icon, you just save the program, and after saving the program, we have to compile the program again. So we go to the terminal, and again we do GCC minus O Euler.x Euler.c minus LM. If you go to the terminal and push the arrow going on top, going upper arrow, you recover the command and you don't need to write it again. So, if you please compile the code again and run the code again and plot the result again, you will see what is happening with the orbit of the galaxy. And GCC, yeah, it's right. Yeah, enter. Then execute. Guardate di Computability. Eso están graficando la 1 con la 2, no que graficar la 2 con la 3. Are you done? Okay. No. Change the ratio of the axis. Entonces tenías que compilar y volver a ejecutar. Y lo volver a ejecutar. So, all we have the figure. So, if you can see, then if you compile, and then you run, you have to compile and then run. If you don't run the program, you have to do nothing. Then you go to close. And then you have this figure. As you can see here, indeed, the particle is leaving from this position in this direction. As we set up the conditions, the initial conditions, the particle is going in this direction, is going far away, traveling to anyway, the closest, to the point of closest approach, periaxis in the orbit. But instead of closing the orbit, it is precessing. The question now is this precession real or is a numerical issue? This precession might be a physical phenomenon. For example, Mercury moves this way, for real. But as we saw before, this particle with these initial conditions doesn't move in this way if you modify the parameter, which is a numerical parameter, not a physical parameter. The physics of the system can change and will change, probably a lot, if you don't do a tuning, if you don't take into account that you must tune the numerical parameters of your simulation. In this case, you change the physical conditions of your problem, in which you have an elliptical orbit, closest one to a different orbit, which is still elliptical, but now precesses, and has every time a different size for the major axis of the orbit. You can see that the size of the semi-major axis of the orbit here is 1, and this one is bigger. This precession is not a physical artifact, it's just a numerical artifact because you are not doing the integration with the real values or with the optimal values for the integration of the equations, which in this case is this delta t. And that's something one has to really take into account. If you run, for example, let's assume I'm running a simulation of the formation of a galaxy or the dynamics of the Milky Way, and I run it with a time step, integration time step of 0.1. With such a huge time step of integration, the orbits of the star are gonna go crazy. Probably the disk is gonna be destroyed, and then I'm gonna assume, if if I'm so proud of my work that assuming that my simulation is completely right, I'm going to assume that I did some extra physics to interpret the dynamics of the galaxy, and that could drive me to wrong conclusions about the existence of these galaxies. For example, Milky Way or these galaxies like the Milky Way might not exist. And then I publish the paper. And then the community come on top of me and tell me, please, first, learn to run simulations. Because one actually needs to make what we call the numerics convergency tests. A convergency test means that you take the parameters of your model, in this case, the parameters of my model or the parameters of my numerical approach is the time step of integration, and you have to change it, to vary it until you find convergency. If you take delta t in the program and you change successively every single time, then we have this value, and then I change it to this value, compile, run, and replot. I have a different result. And I change, if I change in a continuous way the value of the integration time state, I'm going to find a value for which the solution converges to the same situation. When you find convergency, then you can trust your results for the value of the parameter you found convergency. And that's something that is very important, not only for this kind of problem, for any situation in which you are solving a problem using a computer. Because the truth is that the computer doesn't have the truth. Computer gives you numbers. That's all. You interpret those numbers, and then you have to take care of that. Yeah, computer doesn't know anything about physics or mathematics, so you have to take care of it. Is there any question? No. I'm sorry, but we will have no time to play with the rest of the code.
Why you have a condition in time?
That's just aesthetics. No, I do have here a conditional of the time because I mean, I'm doing a lot of do loops, so I'm doing a lot of iteration. If I print a line status of the, let's assume that each point here is the state of the simulation every single time step. That means for each value of delta t. Yeah? If I then use a time step of 10 to the minus 6, yeah, and run it for 1 unit of time, I'm gonna have 1 million of lines in my file. 1 million of lines in my file or in my memory is gonna take, as I was discussing last session, it's gonna take me a lot of hard drive space. And probably I don't need to know all the information about the position of the particle here and here. Because if I already know that the process is quite smooth and homogeneous, then I can just interpolate the result between those 2 points. What I'm doing in this conditional here is just avoiding me to deal with a file of 1.5 gigabytes and have just a file of 50 gigabytes. Just conditioning the frequency of the output of the simulation. Then it's just static or practice. What do we do? We are not going to have time to finish the exercise with the other code. Let's try to do something. I promise I will write a recipe, and with the recipe you can try to follow the rest of the exercise at home or here by your own. I promise I will do it, but I promise I will not do it in the weekend, in this weekend, because I have a lot of work. So once the tutorial is ready, I will send it to you. I will ask Jorge to send it to you, and then you can have it, and then you can play with the other 3 or 4 programs, and you you can know how to use them and how to visualize the stuff they produce. In any case, I hope in this, I mean, the point is that just 2 lectures is not enough to do all we need to do. I hope you just got a vanilla sky of what we do when we run simulations on the body problem. And basically, I'm very happy we managed to this point. Because if you've got this point, you've got the problem. If you understand what this program is doing, you know how to solve the problem. All the rest is just like, I mean, it's like walking. Once you do this thing, you can run, you can jump, you can fall down, you can do everything. But the first things are the more difficult ones. Then, even Wednesday, next week, I haven't said anything, please ask me, and then I will remember I have to do the thing. Please, go home. No, you have to go to the time.